Okay. Um, Hello. This is Sai Dinesh. I am a PMRFTA for E33 Digital Signal Processing course, and this is week 7 live session. So yeah, so this is week 7 live session. So in this class, we'll be talking about inverse DTFT and DTFT of sequences that are not absolutely summable. And then response of LTI systems to sinusoids. Okay, and then next we'll talk about the causality and stability and the properties that are required for the by the that are to be satisfied by the system in order to be causal and stable. And then response to suddenly applied inputs. Response to suddenly applied inputs. Yes. Yeah. Welcome to week 7. Um, so here in this class we'll be talking about so mainly we'll be solving the I'll be giving you hints about the assignment 7, week 7 assignment, and I mean basically these are the topics that are covered in week 7. So inverse DTFT and the DTFT of sequences that are not absolutely summable and then response of LTI systems to sinusoids, the properties of systems like causality and stability, and what are the conditions that are needed to be satisfied for the system to be causal and stable, and then response to suddenly applied inputs, right? So I'll start by writing the DTFT and IDDFT transform pair. So the DTFT of a signal, let's say, okay, let x of n be a discrete signal, and let's say x e per j omega, the DTFT of x of n exists. So in that case, the DTFT of a signal x of n is x e per j omega is equal to summation from minus infinity to infinity x of n e per minus j omega n. So this is the DTFT of x of n, and similarly the inverse DTFT is x of n in the time domain is equal to 1 by 2 pi from minus pi to pi x e per j omega g per j omega n into d omega. So this is the IDTFT, right? So yeah, and then so yes, so this is the basic DTFT and DTFT. Then we'll be talking about the DTFT of not absolutely summable. So DTFT of a signal exists when the signal is absolutely summable. DTFT exists when the signal is absolutely summable, meaning the summation from minus infinity to infinity, absolute values of x of n is less than infinity, right? And second one is square summability. Right, so this is a sufficient condition but not necessary, but then second one is a necessary condition, right? So let's say we want the DTFT. So some signals are there where the DTFT is actually difficult to use, I mean difficult to find out, right? Or the DTFT inversion formula so I mean the finding the IDTFT might be difficult in some cases, right? So example is one which is taught in the class, where x e power j omega is equal to 2 pi delta omega from minus pi less than or equal to less than equal to pi, because this is 2 pi periodic, right? So next one is, so we need to find x of n. So x of n is 1 by 2 pi minus pi 2 pi 2 pi delta omega to j omega n, sorry, d omega. So this 2 pi and 2 pi gets cancelled, so delta of 0 which is equal to 1 for all n, right? So for 1 we have 2 pi delta omega, which is a DTFT pair, but minus pi less than or equal to omega less than or equal to pi. Okay, yeah. So but if we want to, if we do not want to restrict, so I mean basically this whole thing, but DTFT is 2 pi periodic, right? So this actually is x tilde of n equal to 1, then x tilde e power j omega is actually delta of omega 2 pi into delta of omega plus 2 pi k equal to minus infinity to infinity. So this is like a impulse train. So basically if you have samples 1, then you have an impulse train. Two pi, 4 pi, minus 2 pi, minus 4 pi. Right. So this is actually what I mean. So this is actually what is used in sampling. I mean, used sampling, which will be dealt in the later part of the course. Okay. Yeah. So and then like just like we got 1 and 2 pi delta omega. If you want to model it with complex exponential, so this is the modulation property, or you can say a shifting property, 2 pi into omega minus omega naught, right? But we know cos omega naught n is equal to e power j omega naught n plus e power minus j omega naught n by 2, right? So what will be the dtft of cos omega, so of this part, counterpart, will be 1 by 2 into 2 pi into delta of omega minus omega naught plus omega naught, which is pi into delta of omega minus omega naught omega plus omega naught. So basically it is not 2 pi and pi here, because it's like the law of conservation of energy. So the energy is conserved in both equally, split equal in both negative and the positive frequency side. Okay, yeah. So let's do some example assignment questions. 1 second. Week 7, sorry, 7 assignment. So the first question is, a sequence having no Z transform cannot necessarily process a DTFT. So let's start with the assignment. So a sequence having no Z transform cannot necessarily possess a DTFT. Is it true or false? So now a sequence having no Z transform cannot necessarily possess a DTFT. So let's say 1, like xfn equal to n for all 1, which we have already done, right? So 1 means 1 power n u of n plus 1 power n u of minus n minus 1, right? So this is actually not absolutely summable, and Z transform actually does not exist. But does DTFT exist? We just solved here. So what one means, right? So can DTFT exist, right? So yeah, next question. If a sinusoid is given as input to an LTI system, the output will always be a sinusoid. So the LTI system is the important part here, right? If a sinusoid is given as an input to an LTI system, the output will always be a sinusoid. How is it possible? So let's take cos omega naught n. So cos omega naught n is e power j omega naught n plus e power minus j omega naught n by 2. So e power j omega naught n to an LTI system of h of omega will give, since this is an eigenvector, the output will also actually be a will be of the same form, meaning h omega naught into e power j omega naught plus angle of h omega naught into n. So linear sum, what will this be, right? And then you do dtft, I dtft, this will yield a y of n. So is this sinusoid? So e power j omega naught is complex sinusoid being an eigenvector of an LTI system is the main trick here. Okay. Yeah. And third question. Stable anticausal system. Stable is it right? So stable anticausal system has all its poles strictly outside the unit circle. Unit circle, right? So solution. So what is the condition for stability? Condition for stability include unit circle. Now what is the type of ROC for anticausal signal? What is the type of ROC for anticausal signal? So depending on 1 and 2, find the condition on the location of poles and zeros, right? So anticausal actually means, so anticausal means if n equal to 0 for all n greater than for all n greater than 0, strictly anticausal, right? So So basically you need to like see which type of ROC the anti-causal signal has, depending on. So this is the pole, and ROC. So which type of ROC does it have, right? So next question 4 is system with poles both inside both and outside the cannot be stable. So types. So what are the types of ROCs? So first one is it should be connected. So there are three types basically. One is ROC mod Z greater than A. ROC mod Z greater than A, and then ROC mod Z less than B, and then third is mod A less than mod G less than mod B. So if you see, then he said that it has poles both inside and outside the unit circle. So this is the unit circle. It has poles both here and here, right? So let's say this is the ROC, right? And then stability. So they said that in the question, is it cannot be stable. So ROC should include mod Z equal to 1. So is there a type of ROC in which there are both poles and zeros inside now, I mean poles both inside and outside the unit circle, but still include mod Z equal to 1? Right? Find ROC. Next, fifth question. The steady state response of a causal and stable system will contain only input modes. So first let's talk about Right, so let's start detour. Response to suddenly applied inputs. Okay, so yeah, so let's say suppose x of n is applied to an LTI system at n equal to 0, right? So x of z is actually going to an LTI system with the transfer function h of z, and the output has z transform y of z. So now again, let x of z is p of c by q of z, and h of z is equal to b of z by f z, right? So in that case, y of z is equal to x into h equal to p of z, b of z, q of z into a of z, and then we use partial fraction method. We get y of z is equal to k equal to 1 to n x sec c inverse right. So this nx and nh are the number of poles for the z transform of x and z, h respectively, right? So next, assuming causality, we have y of n is equal to ck at k power n u of n, k equal to 1 to nx plus k equal to 1 to nh, again dk poles pk power n into u of n. So this actually is the input modes, this is the system modes or natural modes, right? So system modes means that the inputs, the output corresponding to the specific input, but the natural modes means that even when there is no input, there is still some natural response at the output, and that is known as that is described by the system modes, right? Now fifth question, let's go back to the fifth question. So Q5, so steady state response of a causal and stable system will contain only input modes. So here we have both input modes and system modes respectively, right? So let's say we have x of n is equal to b power n u of n, and h of n is equal to a power n u of n. Then y of n is y of n y, so y of z is actually 1 by 1 minus Az inverse into 1 by 1 minus B's inverse. So this is h of z and this is x of z. Since it is a convolution, it is a multiplication. And then using the partial fraction method, we have 1 by a minus b, a by 1 minus z inverse plus b by 1 minus b's inverse, right? So if you take the ADT of t, we get y of n is equal to a by a minus b into a power n u of n minus b by a minus b power n u of n. So this is the system mode, this is the input mode, right? And in case, just for fun, let's say x of n is also equal to a power n into u of n, like it's equal to, so what I mean, similar to the channel response, then output is z inverse of 1 by a z inverse whole square, which is n plus 1 into a power n u of n. So this is actually resonance. Okay, yeah, so fifth question. Now let's go to the sixth question. Now an ideal low pass filter cannot be realized in practice because so question is that an ideal low pass filter cannot be realized in practice because it violates the Pavlov-Wiener theorem. So is this true? So actually, so what is ideal low pass filter? In the discrete case, we have so this is omega c, the cutoff region. This is x e per j omega, right? So x e per j omega, so h l, let's say hl. So hl e per j omega is actually 1 for mod omega less than omega c and 0 otherwise, right? So what is the time domain of this? I mean, we do ADT of t, so h l of n is equal to 1 by 2 pi minus omega c 2 omega c e power j omega n into d omega, which is equal to e power j omega c n minus e power minus j omega c n by j to 1 by 2 pi, which is equal to sin omega c n by pi n. Therefore a low pass filter will be a DTFT transform pair with the time domain signal Sine omega cn by pi n. So basically we have a rectangular function and then we get a sinc function on one side, right? So that is the same property, right? So and one second. Yeah, sorry. So so a system, sorry, a system uh, which is physically realizable is that sorry, so it cannot produce an output before the input is applied, right? So this is a causal system, right? So the impulse response must be causal, therefore h of t must be causal. At the same time, now in the frequency domain, the criterion that satisfies the criterion for a physically realizable system, physically realizable system is the Taylor theorem, that is integral minus infinity to infinity natural logarithm of magnitude of h of omega by 1 plus omega square into d omega should be less than infinity, that is absolutely integrable. This function should be absolutely integrable. So this is what it means. So does the low pass filter satisfy this? So this is what we need to find in the sixth question. Okay. One second. Is this recording? Hello. Yeah. So next is the question number 7. Just adjusting my mic. Yeah. Now let x of n is equal to sine square omega n, right? Then what is the question? sine square omega n, then is dt of t in the range minus of pi less than omega less than pi is given by is given by so solution. So what we need to find is x of n is what? Sine square omega naught n, right? So we know that cos 2 omega naught n is actually equal to 1 minus 2 sine square omega naught n, which implies sine square omega naught n is equal to 1 minus cos 2 omega naught n by 2 is equal to 1 by 2 minus half 2 cos omega naught n. Now earlier we have done this 2 pi delta omega, which implies 1 by 2 is just pi times delta omega, and then cos 2 omega n is equal to e power j 2 omega naught n plus e power minus j 2 omega naught n by 2. Then find its dt of t and sum it all up to get the final answer. Okay, now next we move on to question number 8. no. A system with real valued impulse response h of n has transfer function h e power j omega equal to 1 minus omega by 2 pi e power j omega and 3 by 2 minus 3 omega by 2 pi e power minus j omega for 0 less than omega less than pi by 2 and pi by 2 less than omega less than pi. Is it right? Yeah. So x of n is minus pi by 3 n plus pi, sine minus pi by 3 input is actually sine minus pi by 3 n plus pi, which is equal to minus sine pi by 3 n minus, which is equal to sine pi by 3 n, right? Yeah, so minus, yeah, exactly. Sine pi by 3 n, right? So x of n is sine pi by 3 n, which is equal to e power j omega naught n minus e power minus j omega naught n by 2j, right? So 1 by 2j e power j omega naught n minus 1 by 2j e power minus j omega naught n, right? And since it is given that h of n belongs to the real part, it means h star of e power j omega is equal to h e power minus j omega. Right? So now all we have to do is find h e power j omega at j equal to pi by 3, which is equal to mod h e power j omega into e power angle of h e power j omega, sorry, omega equal to pi by 3. Right? So you solve this. Solve from the given h of omega. Similarly for minus the negative part. Similarly for the negative part. Right? Yes. So next is question 9. So let x of n is u of n. Okay, what's the question? Let me see once again. Let x of n is u of minus n, then is dt of t is given by. Okay. U of minus n. Right? So let's find for u of n and then solve it. Right? Now let y of n is equal to a power n u of n minus a power minus n u of minus n minus 1. So the dt of t will be 1 by 1 minus a z inverse plus 1 by 1 minus a inverse z inverse and mod a less than 1. Right? Now in the limit a tends to 1 x of n, this is equal to signum function of n, which is equal to 1 for n greater than or equal to 0, and then minus 1 for n less than 0. Right? Therefore we have Sgn of n is 2 by 1 minus e power minus j omega. Right? But excuse me, is it recording? Hello, yeah. But actually u of n and signum of n, signum function are related. How? So u of n is actually equal to 1 by 2 of 1 plus signum function of n. Right? Therefore u of e power j omega, the dt ft of u of n is equal to 1 by 2 of pi 2 pi times delta omega plus 2 by 1 minus e power minus j omega. So we have dt ft of u of n. Find dt ft of u of minus n using the dt ft properties. Okay. Yes. So next is the 10th question. Question number 10 says the LTI impulse response HFN is equal to 2 times 1 by 2 power n into u of n plus 2 times 2 by 3 power n u of n, right? And the input is x of n is equal to 3 times 1 by 2 power n u of n plus 2 by 3 power n into u of n. Find y of n. This is the question. Solution: find h of z comma x of z. So h of z is, let's just write it again, 1 by 2 power n into u of n plus 2 into 2 by 3 power n into u of n, right? So since it is causal, because we know that it is multiplied by u of n, it will be equal to 2 into 1 by 1 minus 1 by 2 into e power minus j omega plus 2 into 1 by 1 minus 2 by 3 e power j omega. So this is equal to h of z. Similarly, what is x of z? 3 into 1 by 2 power n into u of n plus 2 by 3 times u of n. Sorry, this is x of n. So if we want to find the x of z, which is 3 into 1 by 1 minus 1 by 2 power e power j omega plus 1 by 1 minus 2 by 3 e power j omega, right? And then step 2, y of z is equal to x of z into h of z, right? So multiply times this. Okay, so here we'll get like squares, and then you need to, next step 3 would be find RDTFT of y of z. So straightforward. Okay, so next is question number 11. Says that let me just open this one sec. 11th question says that let x of omega denote the DTFT of the sequence x of n is equal to 4 minus 3 minus 5 minus 3 and 9. So this is n equal to 0. Next, consider P of n and P of omega be a DTFT pair, where actually P of omega is x of minus omega, and then Q of n and Q of omega be another DTFT pair where u of omega is actually e power minus j omega d of x d omega by d omega, right? So now this is now actually we know that the relevant, so let's try the relevant DTFT properties. Now relevant DTFT properties are actually, if we have h of n, now let's say h of n and or a DTFT pair, then sorry, h of minus n is equal to h e power minus j omega. That is first one, and second one is n times h of n is equal to j times the derivative of the DTFT. So using these two properties, find P of n and Q of n. Then finally find the value of P of 1 minus Q of 3 whole square. Okay, yeah, so these are the assignment questions, and yes, so in this live session we have talked about the inverse DTFT. Like, the topics that are covered are the inverse DTFT and the DTFT of sequences that are not absolutely summable, and then we talked about the response of an LTI system to sinusoids. Oh, 1 second. To sinusoids. Then we talked about the causality, stability, and the response. Causality and stability of a system and the response to a suddenly applied input to LTI systems. So LTI systems actually. Yeah. So this is the DTFT and IDTFT pair that we well know. So 1 by 2 pi minus pi to pi x e per j omega into e per j omega and d omega gives the IDTFT of the x e per j omega, which is the DTFT of x of n, right? So DTFT exists when it is absolutely summable or at least square summable, right? And then this is an example which we talked about. So here we have a signal 1 which is constant DC signal, but still we have a DTFT. This is 2 pi into delta omega, right? So actually we know that these have a DTFT because if you take the Z transform, actually Z transform does not exist, but then DTFT does exist in this case, right? And then DTFT, and since DTFT is 2 pi periodic, and here we are mentioning that this belongs to minus pi to pi, in order to extend it we brought it from here to a transform pair. So basically a discrete signal actually gives a transform pair, and this is what we'll be seeing in sampling later, right? And then we discuss the assignment questions. So yes, please let me know if you have any doubts in the assignment questions.